Capital Technology University, established 1927. Educate, innovate, inspire. Topic, problem, purpose. Time's existential relation to mass within Newton's second law. Presented by Doctoral Programs Shashwat Khatri Chetri, KC, PhD in Aeronautical Sciences, November 2025. Topic, overview. This study explores time as a foundational context of motion and force, establishing its direct role within Newton's second law and its broader implications in aeronautical and computational systems. A core objective of aeronautical sciences design is to displace the greatest amount of distance in the shortest duration possible. The problem exists within the broader context of modern applied physics, where despite Einstein's relativity linking time to motion and gravity, as well as Heisenberg's uncertainty principle revealing its interdependence with momentum, time remains treated as a passive parameter both in quantum and classical studies of motion. In aeronautical and computational systems, this limited view constrains optimization, accurate modeling of lift, thrust, drag, and processing efficiency requires recognizing time as a dynamic factor that governs force interaction, synchronization, and overall system performance. Advancing the understanding of time as an active design variable could improve predictive modeling and control in aeronautical systems, enhancing efficiency, stability, and energy management during dynamic traversing conditions. In computing and chip architecture, time-aware and quantum-related frameworks have demonstrated measurable gains in performance and energy efficiency, suggesting that similar principles could transform aeronautical engineering and control systems. As modern aerospace platforms increasingly integrate advanced intelligence, distributed computing, and real-time analytics, redefining time as a governing variable rather than a background constant is both scientifically warranted and technologically necessary. Problem. The problem to be addressed in this study is the absence of time as an explicit applied variable in the foundational equations and control systems that define aeronautical and motion optimization. While Newton's second law establishes acceleration as the rate of velocity change with respect to time, current aerodynamic and computational models often treat time as a background constant rather than a dynamic parameter shaping system behavior and responsiveness. As a result, relationships between lift, drag, thrust, and power are modeled primarily through static or steady state conditions, overlooking the critical temporal derivatives that define real-time flight dynamics. This omission affects aerospace engineers, control system designers, and computational modelers who depend on predictive algorithms to sustain flight equilibrium amid rapidly changing conditions. Without treating time as a functional control variable, current models cannot fully capture how flow, drag, variation, and lift response evolve moment by moment within dynamic atmospheric environments. This temporal oversight diminishes model precision, restricts energy optimization, and weakens autonomous response calibration during time-critical operations. If time continues to be overlooked as a mere constant rather than a numerator of an interval derivative across aerodynamic systems, the field risks continued energy transfer inefficiencies in propulsion design theory, reduced domain traversing stability in physically rigorous environments, and diminished integrative control in next-generation motion-optimized vehicles and computational designs. Such energy efficiency losses result in unrealized work, thus making life more difficult on the average person. Energy losses create a broader system of demanding tasks on the individual to keep up with energy requirements. Aeronautical sciences has the ability to alleviate time energy loss through efficiency. Purpose statement. The purpose of this mixed methods exploratory study is to analyze how treating time as an active derivative variable within Newton's second law and related aerodynamic equations influence system stability, energy transformation, and control responsiveness in aeronautical and computational models. The study seeks to reveal how temporal derivatives, present but often underutilized, can enhance real-time modeling accuracy and domain performance. Connection to the problem and research questions. This study provides a direct and logical response to the identified problem by constructing a time-dependent analytical framework that explicitly integrates d over dt in terms of lift, drag, thrust, and power equations to capture the evolving nature of flight stability. This approach aligns with the research questions exploring how time's dynamic role as a variable improves predictive precision, optimizes energy efficiency, and establishes a unified foundation between aeronautical physics and computational timing systems, advancing both theoretical and applied aerospace design. Step-by-step overview of the study. Literature review. Examine existing Newtonian relativistic and computational models that define force, power, and stability without explicit temporal modulation. Differentiate the word time in consideration to iteration and repetition. Model development. Create an aeronautic system. Extend F equals ma and P equals dE over dt to model maximal velocity, variable A, and maximal water velocity, variable B, and maximize C equals A plus B such that in a use case, an aeronautic system is maximizing C while A and B are equal. Computational model of an aeronautic system mass across air, under surface water, and transition dynamics to test velocity equivalence with respect to time as the or a primary paradigm variable of observables. Data collection. Record maximum velocities, power, demand, drag, and stability metrics to evaluate A, B, and C while utilizing the essential nature of time hidden within classical mechanics. Data analysis. Apply correlational and regression methods to assess relationships between time variable parameters and system performance outcomes. Validation. Compare simulation results against established aerodynamic data sets and assets for accuracy and repeatability. Conclusion. Determine how time-integrated equations improve model fidelity and propose guidelines for time-aware systems design in future aerospace and computational applications. This project concludes by identifying a shared limitation in both aeronautical sciences and quantum mechanics. Classical systems are bounded by Newtonian constraints, while quantum systems are bounded by the uncertainty. The proposed research introduces a unifying framework by setting maximal velocity equal to maximal underwater velocity, creating a symmetric condition that exposes how motion behaves across different mediums. Within this model, time is elevated from a passive measure to an active variable, enabling reinterpretation of acceleration, drag, and resistance by treating time as the bridge between macro level aerodynamics and micro level quantum behavior. The research presents a pathway for reconciling classical and quantum limits and expanding the design space for future aeronautical systems. Systems in which the positive externalities help the general population of the common person, of the individual,